just started going real far. You put your thumb over the front of it and made it smaller, doofus. Right? Now, you knew that. How do you make air come out of your mouth faster? When you whistle. You make that opening smaller, push the air through, it has to come out faster. And actually, it oscillates. It comes out so fast, it'll oscillate and make a sound. Like that. So it's faster there. Now, how much faster is it? How do we figure out what's it depend on? Well, it actually just depends on the area and the initial velocity flow. Because what we can say is the equation of continuity is that area 1 times velocity 1 equals area 2 times velocity 2. So if area 1 is big and velocity 1 is relatively small, then area 2 gets small. To make these two equal, velocity 2 has got to get big. It's got, because these numbers have to equal each other. So when you make pipes bigger, fluid slows down in it. You make pipes smaller, fluid goes faster in it. And you know this another way. Assuming you put it in the woods or hang around on creeks and rivers. Up in Caldwell County where I grew up, there's a place called, up on Wilson's Creek up there, a place called the Chute. And that's where the whole river, and the rivers maybe as, it can be anywhere from 30, 40, 50 feet wide at times. It's not very deep, but still it's pretty wide. It pretty much all goes it gets funneled between these two big rocks that have fell, of course. But it's basically down in the middle of these two ridges. And these rocks are maybe 6-8 foot apart total. And the whole river goes through right there. Now for that to happen, does that water have to move really, really fast? It was big here and kind of slow. Now it's narrow. Water shoots through there. They call it a chute for a reason. You shoot right through there, you could say. Now, a lot of people like to do that with like a canoe would be really dangerous. I forget what it's called. But bottom line, you go right through it. You can body surf through it, right? Kayak. If you're not careful, you come out there so fast, and when it goes out, it's turbulent flow. In many places, if you're not careful, it'll turn you over. You'll get stuck. When I was growing up, you see about 1 or 2 people a year dying trying to go through the chute in either a canoe or a kayak or body surfing it or whatever. Not too smart. Normally, there was alcohol involved in a lot of those instances. That's where a lot of people did up there. But you know it. If your river's moving faster, it's probably going through a narrow area. When it widens out, it goes slower. It's simple. If you ever go tubing up on creeks or anything, you notice the same thing. Equation of continuity. Makes sense. And the other one is Bernoulli's equation. Of course, Daniel Bernoulli came up with it. And Bernoulli's equation kind of summarizes everything you see for fluids. Now, what he basically says, what would make a fluid go faster? It would neck down. What if it's going down a hill? If it's the top of a hill or the bottom of a hill, it goes faster, right? Makes sense. Just like a sled, fluid does the same thing going down a hill. And it would also depend on what the initial pressure is pushing it through there. So what Bernoulli said was, if you've got a pipe like this, and here it's higher up, so it's at some height, some h, we'll call it height. I think it's what he uses here. We'll call this, let me call this Y1 or Y. We'll just use some Y because I'm going to give you the formulation that makes sense. So it's some Y there. That would be going through the middle of that. And you've got some area here. Some area 1 here. Just some area here. just some area. And it's got some the fluid's coming in with some initial pressure. Some P initial. And of course, it's going through here and comes out there. Now, what he says is, Bernoulli said, was that at any point in the pipe, that the initial pressure, we'll say P initial, plus rho gy, which is just pressure due to the depth. It's like static fluids. As it goes down, you got more pressure on it. So the pressure that it's initially at, plus the pressure due to depth, plus the pressure due, it's flowing, it's got pressure, plus the pressure due to the flowing, which is 1/2 rho v squared, where v is the velocity of this. Velocity v. And all that equals a constant. And anywhere in this, the initial pressure plus the depth pressure due to how deep or how high, how far you are, how up or down, how far you've came down, plus basically the moving pressure. Due to it moving, there's pressure on it to try to push it due to that. And all that equals a constant value anywhere in the pipe. Anywhere in the pipe. Now, normally, they'll start this out and say, well, compared to this point, if you know all this stuff here, what is it? What's the velocity down here? Or something. That's what they try to. A lot of times you'll see what's the change in velocity. If it's going here, then flows uphill to there. That's one of the examples in the book. And from the areas you're able to get, and you have to normally use this equation of continuity to find the velocities, and then you use that to get the heights. And, maybe you're trying to find the initial pressure. I don't know. But these are the two equations you use. Now, there are a couple examples in here. You did some stuff on the lab with moving fluids. The examples in the book, 1411 and 1412, very good examples. Okay, so I would definitely look over them, write them in your notes, figure out how they work. Those are good examples to demonstrate what I'd like you to get with Bernoulli's and equation of continuity, which basically governs fluid dynamics. There's a whole lot more of this. This is just for ideal fluids. Can't be compressed. No resistance to being pushed or moved like that. No viscosity, you would say. And also nice straight line laminar flow, as you saw when I burnt the napkin. It went up straight, and it doesn't start swirling around or making little curly cues there, so it's because it's not turbulent flow. And with your rocket, one of the things I ask you is put your hole for your altimeter 3 inches or so below your nose cone, because the air goes over that nose cone. As the air would go over the nose cone, initially it's going to want to come up. But if it's got straight for a while, any little turbulences kind of work themselves out, and it's still not going nice and straight. these altimeters need laminar flow, because what we find is if it's moving over it in a laminar method, it reduces the pressure at that point, and that's a different class. But by reducing that pressure, that's directly related to that way that as it moves over it. What I'll say is, as it moves over it, it doesn't change the pressure due to the altitude that you're at. It does reduce it a little, but you can take that into account with these altimeters. Okay, so fluid dynamics, Bernoulli's principle, equation of continuity, laminar flow demo. Hope you enjoyed it.